Hello everyone, welcome to GIS Man. I'm Miles Lee. Previously, I've talked about some topics of ArcGIS, GIS Web Development, AWS, as well as database. And from this week, I'm going to talk about some FME topics. Actually, I like FME very much. As you can see, I've done lots of FME projects. And I use it for data analysis, the process automation, as well as some very complex GIS algorithm design. And personally, I'm also the FME certified professional. So let's get started of today's topic. Today I'm going to show you how to modify the custom transformer and combine with the Python in the PythonCaller to do the linear referencing. For the concept of linear referencing, you can find it on ArcGIS documentation, which is described very clearly. And for those who don't really know what it is, I can just give a quick example. For example, this is a long polyline which has only one geometry, what we call the route geometry. And after the linear referencing, it can be turned into the multi-section geometry with different geometry shape. For example, in layer 1, it will become the shape like this. In layer 2, it will become the shape like this. What you can see is that the shape of layer 2 is quite different from the shape of layer 1. This is the result of the linear referencing because the result is based not only on the input geometry, but also based on our input value of the distance. For example, layer 3, you can see this section is pretty long, but in layer 2, it's quite short. And also in layer 1, it's quite different. So this is the result of the linear referencing. In ArcGIS, we do have some ways to do that. For example, like using the toolbox called make route in main layer. But however, this time I would like to show you how to do that in FME by simply modify the existing custom transformer. So let's get started. Firstly, we will need to build up a standard simple read process and write output framework. So what we need is to have a feature reader to read in our input geometry. And after that, we will need to have a process block, which is our to be modified custom transformer. But currently, I just copy and paste it right here and line it up. And later, we will need to have a length calculator as well as the attribute rounded. We will need to use these to check our output is correct or not. If the geometry shape is as same as our input distance. And finally, we will need to have a feature writer to output our results in GeoFile database. We call the output as layer 4. Okay, so now the key thing is to modify the logic inside the custom transformer. We need to right click on the edit button to turn it on, and then we're going inside the custom transformer. What we need to do is to firstly evaluate what needs to be changed. Firstly, we start with the published parameters. According to our requirements, we don't need to have the mode, we don't need to have the value, because we will, the mode, is shortened to following length, but actually our requirement is to define our dynamic length section in the geometry, so we don't need this one. And also the value is the line length, the fixed line length for the specific geometry, but actually we don't use the fixed line length. Our length are dynamic based on our input, so we also delete this one. But we do need the distance, which is not here yet. The distance is to define the geometry shape, how long for each geometry. It can be like this, or it can be like this and this. Yeah. So what we are going to do is to add these parameters for our custom transformer. So we can do it right here. This is the attribute creator. We don't need to have the mode, so we delete it. We don't need to have the value, so we delete. But we do need the distance parameter. So we need to have the distance parameters for our input. Let's see, and then here we will need to have our own user parameters. We call it the distances, and the pop-up we can give it anything like chop by distance, separate by comma, for example. And this is our published parameters. And after that, we will need to change our code logic inside the PythonCaller. What we are going to do first is to evaluate, for example, like what attributes is needed and what attribute is not needed based on our input published user parameters. So we've already deleted the mode, we've already deleted the value, because according to our requirements, we don't need to have the fixed mode and the fixed length value of our linear referencing geometry. So we just delete it, and we do need the distance to define our dynamic distance length geometry. So we need to define it right here by using the feature get attribute line divider dot distances. Okay, and after that we can also see the original author, he does not want these kinds of attributes to go to the following process. They are redundant, so he deleted. So we can follow this logic to delete the redundant attributes. For example, of course, the mode is already not exists, the value is already not exists, so we just delete it right in the array. But we will need to also delete the distances like this attribute. You see, we delete these redundant attributes. And then the for loop will help us to do this job. We will feature remove attribute, and this attribute will not be shown in the following process and following transformers. And after that, we will need to find out which logic block we will need to change to implement our linear reference. In the original code, we can see that this section is used to chop the curve and polyline. It uses the begin position and the end position, and the end position is always one step more than the begin position. That's why I say, this original custom transformer just chop the lines into the fixed length, but not the dynamic length. And then after that, the original author used the curve.snip function, which is the function of the FME objects, to cut the long polyline or curve into a single section. So this is also needed later, and that's why we will need to change all of this block. These are our targets. This is our target. So we start to do that. Firstly, what we need to do is we need to split the string of the published parameters distance into array. Distances, and then we need to split that by comma. Actually, the input will be like, for example, 200, 500, 1500, and 1000, and then 2000, something like this. So this is the input string distance defined by the user. So we need to split it by the comma and put it into array. And after this, we will need to give a star position and a star index. And with the index, when is smaller than the number of our input distances. For example, from 0 to 1, 2, 3, 4, 5, the 5 distances. If the index is smaller than 5, so we will be going into our loop block. The beginning positions will be the star position. The end position will be the star position plus the offset of our distance. So which means, for example, like the star position, the first round will be 0, and then the end position will be 0 plus 200, and it will be 200. And the second round will be the star position will be now 200, and then our distance will be 500, so the end position will be 700. And here there is an exemption. The exemption will be, for example, in a very last number, the user input a very large number, which makes the geometry ends longer than the original base geometry. For example, the original base geometry is around like around 40,000 4,000 meters, so it's longer than that. And in that case, we will need to cap it. We will need to cap the end distance as the length of the original base geometry. Right? This one, for example, we can say like give you a bit more. Later when we test it, we can see the similar results as what I described. And after this, we will need to use the snip functions in FME objects. We will need to use the curve.snip, and then this is the embed FME objects functions. Snip distance, and then it's 3D. This one, I mean, this function, this one, I mean, we don't need that actually, because definitely we don't consider the 3D. And then we need to have the begin position and the end position as we define right here. Okay. So after this, the star position will need to be self-incremented. Which means that, for example, the first round, the star position is 0, but after the first round, it will add 200. The next round star position will become 200. And then the next round will be 200 plus 1000, which will be 1200, and so far so forth. The index will also need to be self-incremented because it's inside a loop. This one is used to control if the process jump out of the loop or not. So this is what we need to do. And after this, I think everything should be okay for the code. And here is red because we doesn't expose the right attribute. We need to expose the right attribute and then click OK. I think that everything should be okay now, and we can start running and take a look at the results. Had a finger cross. Something wrong. Let's see. The name mode is not defined. That's what we delete, the publish parameters. We delete the mode and we delete the value, and in the attribute creator we don't use that as well. So I mean there is no attribute called mode. But however, here we still remain the previous author, the original author of these custom transformers definitions. We need to find out the redundant attribute and delete it. Yeah, it's right here. You see the mode, because we have already deleted the attributes right here before, and we forgot to delete the calculations using the mode right here. So we need to delete all of this, and this time should be okay. Let's have a run. Could not convert string to float. Let's take a look again. There should be nothing wrong here. Yeah, we just convert the flow of our distance. But I think the problem is because when we run it, we didn't really define our distance. So I mean, the input will be the empty string, and of course the empty string cannot be converted to the float. So now we define our distance right here, and we can take a look at our examples values right here: 200, 1000, 15, 10, 2000. Okay, let's take a look. 1000, 15, 1000, 2000. Okay, so this time let's run it. Everything should be okay, I guess. Yeah, translation was successful. So let's take a look at our results. Refresh our GDB, drag in our feature class. So now this is our new linear reference results with 5 output. The first one length is 200, and then the second section is 1000, and then the third one is 1500, and then 1000 again. The last one, the last bit will be 500. The last one is interesting, as what I said before. If you see, because our input was 2000, but it's too long. It's longer than our original base geometry's length, so it will be kept. It will be kept to the end of. It will be kept to the length of our original geometry, original base geometry. So yeah, everything is within our expectation. The result is correct. So that's it. This is a topic of how to use FME and modify the custom transformer to implement the linear referencing. So hopefully you like it, and thanks for watching. See you next time. Bye.